Hello, welcome to Math 1324. This is Chapter 10, Section 3, Example 4, I believe. And in this example, we want to use synthetic division to find zeros of the following function. Now, the reason that I want to do this, first of all, is because I want to practice finding zeros. And effectively, finding zeros really does mean just taking the function and setting it equal to 0. And you may be wondering, how in the world am I possibly supposed to do this? The honest answer, truthfully, is very carefully using the calculator. And so what I did before I even started this video is I went ahead and graphed this on the calculator. And I will show you that at the end of this so you can see it. But I found some zeros using the calculator. And looking at the calculator, it showed me that -3 is a 0. Now, here is what you need to do in order to use what's called synthetic division. Synthetic division will help us to find zeros. And there is a theorem in mathematics that says f of k equals 0 if k is a 0. And it's technically more of a definition, so I'll put that double F on there. That's not a mistake. That actually means if and only if. Now, there's another thing that we have called synthetic division. And synthetic division basically says some polynomial divided by x minus k can be done using this process that I'm going to show you. But what's great about that is it says if the remainder, well, let's say it this way. The remainder of dividing f of x by x minus k is f of k. So what that really tells me is that if I use synthetic division and I have a remainder of 0 at the end, then the value that I'm looking at is in fact a 0 of that function. And it actually tells me that x minus k is a factor of that function. So what I'm going to do is I'm going to use synthetic division here. And to do so, here's what we're going to do. I looked at the calculator and the zeros are the following: -3, 1, and 3. So I'm actually going to prove those. I'm going to start out with that -3, and I'm going to use what is going to look to you probably a lot like an upside down division symbol. And then I'm going to use coefficients of every single one of the degrees. So we have start out with the 2 for the 2x to the 5th, start out with the 2 for the 2x to the 4th, and then -28, then -12, then 90, then -54. Good. Now, if you're missing any degree, in other words, if there was no x cubed here, I would have needed to make sure there's a 0 there for that x cubed term, because you need to account for every single term. And here's the process. Technically, there's a 0 here, so 2 plus 0 is 2. And then what we do is we multiply. So -3 times 2 is -6, and that's what I write there. And then we add 2 plus 6 gives me -4. And then again, we multiply this number again by -4. So -3 times -4 gives me this +12. Kind of see what's happening. It's multiply, add, multiply, add, multiply, add, multiply, add. Then we have -28 plus 12. That would be subtraction, which makes that -16. Then -3 times -6 is +48. Then -12 plus 48 is 36, I believe. -3 times 36 is -108. And then add here, 90 plus -108 is 90 minus 108. What would that be? 18. -18. And then negative 3 times negative 18 will be positive 54. And negative 54 plus 54 is 0. Awesome. So what I just did is I just proved that this negative 3 is a 0 of this function by getting a 0 for my remainder. In other words, what that's telling me is that f of 3 is equal to 0 here. And I will talk about this here in just a second, but negative 3 is actually used as a 0 at least more than one time. So I'm going to actually continue this again, and I'm going to use negative 3 again. And I'm just going to continue. Bring down the 2. Negative 3 times 2 is negative 6. Negative 4 plus negative 6 is negative 10. Negative 3 times negative 10 is positive 30. Negative 16 plus 30 is 14. Negative 3 times 14 is negative 42. 36 minus 42 is negative 6. Negative 3 times negative 6 is positive 18. Awesome. So I just proved that negative 3 is a 0 again. In fact, the negative 3 is used as a 0 twice here. If I did this again, if I did this a third time, it wouldn't work. Let me go ahead and show you that. Don't write this down because I'm not going to keep it, but I will show you that negative 3 cannot be used again. So bring down the 2, multiply, add. Multiply gives me 48. 14 plus 48 is 62. Negative 3 times 62 is negative 186, which gives me negative 192. Notice that this is not a 0. So negative 3 is not used as a 0 again. It's just used as a 0 twice. Okay, good. So I just proved that negative 3 is a 0. In fact, I did it twice. Now let's look at the 1. Bring down the 2, multiply, add, multiply, add, multiply, and add. Awesome. And yes, the 1 is in fact used as a 0 one more time. So bring down the 2. 2 times 1 is 2. Add, multiply, and add. Awesome. So that's a 0 twice. And just to show you, it won't be used as a third time because notice you would get a negative 4 out of that. Instead, we need to go ahead and go back and look at the last one, which is 3. So I'm going to use a 3 here. Oops. Bring down the 2, multiply, add. Awesome. Do not use this as a 0. Nothing down here will ever be a 0. All this is the leading coefficient. It's that number there. That's all it is. So that actually tells me that the zeros here are negative 3, 1, and 3. And notice that some of these were used more than once, some of these were not used more than once. And that is actually referring to what's called multiplicity. So the negative 3 has a multiplicity of 2. The 1 has a multiplicity of 2. And the 3 has a multiplicity of 1. And this really does matter because it actually changes the way that the graph behaves at the zeros. And so the behavior at the zeros are determined by their multiplicities. And multiplicity just means the number of times a 0 is used as a 0. In other words, the factor that goes along with it, how many times should you write it down? So in all honesty here, I can actually factor this entire polynomial as the following. Because we have this negative 3 as a 0, that means that x minus a negative 3, in other words, x plus 3, is the factor that goes along with it. And the exponent will be a 2 because I would have x plus 3 times x plus 3. That's what multiplicity means. It needs to be written down twice. And this 1 has a multiplicity of 2, so the factor is x minus 1. Multiplicity 2 means it's written down twice, so the exponent will be 2. And then this 3 here, the factor is x minus 3, and the multiplicity is 1, so technically it has an exponent of 1, but we don't like to write that. We're almost done. The only thing we need to make sure we account for is the leading coefficient, which will be right there. And this is actually the factored form of this. So congratulations, we just factored a degree 5 polynomial function. All right, I'm going to go ahead and go to the calculator to kind of illustrate some of these things that I've shown you. I'll see you there. Okay, welcome to the calculator. You should already see, this is actually the graph of the function. This is in the standard window. If I go to y equals, I just typed the function in. So here's the graph. And the way that I can tell a few things here. First of all, notice that this is actually going to reach that -3. This is reaching 1, and this is reaching 3, because these are going by 1s. If you want to see the table, go to second table. And notice that if the zeros are integers, you're going to see zeros for your y values. But if the zeros were between the integers, then you wouldn't see zeros on the table there. Now, the reason that I can see this, first of all, -3, 1, and 3, the function is getting to be 0 at those points. And what I mean by that is notice that this function is going up to the -3 and then just bouncing back off. And what happens if it just kind of goes up towards it and then bounces back off on either direction, then that multiplicity will be even, which means it has a minimum multiplicity of 2. So it'd be 2, 4, 6, 8, so on and so forth. Same thing happening here. That's a minimum multiplicity of 2. But notice that here, this function is going up and it's actually just crossing kind of in a linear fashion. In other words, if I was to zoom in right here, I would see nothing but a straight line. And so that is, in fact, the reason that it has a multiplicity of 1. So notice that this kind of looks quadratic. Quadratics have degree 2. This looks quadratic. Quadratics have degree 2. This looks linear. Linear has degree 1. So multiplicities are kind of a zoomed in degree of what you see at the 0. Also, another thing, if you add up the multiplicities, 2 plus 2 plus 1, that should equal the degree of the polynomial, which in this case is 5. So it is 5. And that's only really the case if you have all real zeros. There is the possibility of having non-real zeros. So if you add up all of the multiplicities plus any non-real zeros that you may have with their multiplicities, you will always get the degree of the polynomial. Alrighty. Well, there you go. I'll see you in the next video. Have fun.